Hi everyone, in this video we're going to be talking about instantaneous velocity and instantaneous acceleration, and we're going to be finding them from graphs in a very similar method to what we covered in the previous video. So, instantaneous velocity is the slope of the tangent line on a displacement versus time graph, and instantaneous acceleration is the slope of the tangent line on a velocity versus time graph. Acceleration can be qualitatively determined from a graph of displacement versus time by examining the concavity of the graph. I'm going to say that these first 2 points are much more important than this last little point here. Okay, so instantaneous velocity. It's far more useful to define the instantaneous velocity than the average velocity. The instantaneous velocity is the velocity associated with a specific instant in time as opposed to a time interval, and is the velocity measured by your car's speedometer, or really your car's speedometer plus its compass if you have a compass, because velocity includes both magnitude and direction. But when we're talking about average velocity, we really do need a time interval. We need to say, oh, it's the average velocity from, 2 minutes to 8 minutes, something like that. But the instantaneous velocity, you say, what's the instantaneous velocity at 4 minutes? You don't say, say 2 different times or a time interval. So, unlike the average velocity, we must use graphical methods to compute the instantaneous velocity if we're not using calculus. To find the instantaneous velocity, we merely calculate the average velocity over a very short time interval. So, on a graph of displacement versus time, draw a line that touches the graph at only a single point. This is the tangent line. And then compute the slope of this line. The slope is the instantaneous velocity at the chosen time. Okay, so what does that mean? Here's an example. Find the instantaneous velocity at t equals 2 seconds in the graph below. So here's a nice graph of displacement versus time. We have what's kind of a nice smooth curve, and we have it graphed through about 3 seconds. So I could, for example, well, let me start by saying that it asks for the instantaneous velocity at t equals 2 seconds. At t equals 2 seconds, it happens to be at 4 meters, but we're not going to use that information for the most part. What we are going to use, though, well, let me start by doing an approximation. So I could pick some later time, I don't know, maybe like up here, close to 3 seconds, and I could find the instantaneous. Let's do it in light blue. Okay. I could find not the instantaneous velocity, but the average velocity from 2 seconds to what looks like, 2.8 seconds. That's an approximation to the instantaneous velocity. I could also find the average velocity from, what looks like 1.5 seconds to 2 seconds. That's going to be another approximation. And in this case, oops. So that this line has to go through 2 seconds as well. Okay, so these are both secant lines. They're both approximations to the instantaneous velocity. This line's a little bit low. This line's a little bit high. We're looking for one that just touches the curve at a single point. That's the tangent line. Well, I'll keep those up for now. Okay, so we draw that tangent line. I happen to know how I want to draw it. And let's take a look at how I did. So here's the tangent line that I've drawn. I'm going to erase those 2 secant lines that are approximations to the instantaneous velocity. And there we go. It looks like I may have crossed the curve a little bit. I could adjust this just slightly. All right, there we go. Now, I think you'll agree it's pretty close to being tangent at this point. It's just grazing that part of the graph. The fact is that when you do these problems, just like me, you're going to be kind of eyeballing it and doing your best to draw a tangent line. And so there's going to be a little bit of wiggle room as to whether your tangent line is actually tangent or not. And so different students are going to get slightly different numbers. So what I'm going to be looking for is if you're very close to the right answer, not that you're exactly right, not that you're perfectly correct. Okay, so let's find the slope of this line. we'll go from, draw a triangle like this. It is often helpful to pick points that are farther away, but at least for this problem, I'm just gonna work with this this portion of the graph here, and it goes from the slope of this line. The rise is from 0 meters down here to 4 meters up here, and so it's 4 minus 0, and that's 4 meters. And the run is 1 second to 2 seconds, or 2 minus 1, which is 1 second. Your velocity, it doesn't need the vector sign, but your velocity, not your average velocity, but your instantaneous velocity, so I don't put a subscript on it. Your instantaneous velocity at 2 seconds is the rise divided by the run, which is 4 meters divided by 1 second, and that's 4 meters per second. All right. And that's it. That's all we do for the instantaneous velocity. What about instantaneous acceleration? Well, I hope you're seeing a pattern by now. Just as we did with the instantaneous velocity, we can define the instantaneous acceleration, which is the acceleration at a specific instant. Again, not over a time interval, as the average acceleration over a very short time interval. In fact, using calculus, we would say that it's an infinitesimally small time interval, but for your sake, you could just imagine it as being over a very short time interval. And to compute it from a graph of velocity versus time, we do pretty much exactly the same thing that we just did. Draw a line that's tangent to the graph at the time in question, and then calculate the slope of this line. And this is your instantaneous acceleration. Here's an example. Find the instantaneous acceleration at t equals 1 second from the graph below. Well, here's t equals 1 second. It looks like this object, whatever it may be, is traveling at maybe about 10 meters per second at that time. Again, I'm going to kind of avoid using 10 meters per second in my calculations. We draw a tangent line. I could draw some secant lines, but I'll spare you that piece. This looks like a pretty good tangent line. It just about touches the curve at just a single point. And let's find the slope of this tangent line. So, what I'm going to do is I'm going to pick this point, and I'm going to pick this point. So I'm going to be good and use points that are kind of at the extreme ends here. And so what I get is draw a triangle, and the rise is, looks like it's maybe about 14 meters per second down to, I'll say 2 meters per second. So 14, it ended at 2 meters per second and started at 14 meters per second, and so that's 2 minus 14 is negative 12 meters per second. Okay, gotta be careful. It needs that negative sign because this is a downward sloping line, right? Okay. And the run is 0 seconds to 3 seconds, so it's 3 minus 0, which is 3 seconds. And your acceleration is the rise over the run, which is negative 12 over 3, which is negative 4 meters per second squared. Okay. Again, you might get some slightly different numbers. This looks like it might be closer to 3 meters per second, but I actually just wanted the numbers to work out kind of nicely, and so 2 meters per second is a fine approximation to the velocity at this time. But what makes the approximation especially good is that I picked 2 points that were far apart. If you use 2 points that are really close together, then if you don't measure them exactly correctly, then you can get wildly fluctuating estimations for your slope. So use points that are far apart on your graph. Okay. let's talk about kind of putting this all together and graphing displacement, velocity, and acceleration. So if we begin with the graph of displacement, we can find the instantaneous velocity at all times by considering the slope of the tangent at each point on the curve. And we can then use this graph of velocity to find the acceleration at all times by, again, considering the slope of the tangent at each point on the curve. If you're given a graph of displacement versus time, you should be able to produce graphs of velocity and acceleration as well. So I'll walk you through what that might look like. Example, use this graph of displacement versus time to sketch corresponding graphs of velocity and acceleration versus time. So here's an object. I've left out units and everything. This is just going to be kind of a qualitative example. So no numbers involved. And so we have some object, let's say it's moving horizontally, and so it's moving to the right, and it's moving more and more to the right, and then it reaches some peak position, some rightmost position, and then it goes back to the left, and it reaches some leftmost position, and then it continues off to the right. So maybe I can try approximating that down below the graph. So if you follow my mouse cursor, it does something like this. It goes to the right, and then slows down and stops, and then goes back to the left, and then slows down and stops, and then goes back to the right and speeds up and goes off somewhere. Okay. So here's that same graph. I just copied it from the previous page. What you're going to do is you're going to look out for some very key points. I want you to first identify places where the slope of the tangent is horizontal, where the graph levels off. And so I see one point right here and another point right here. And so identify those. Those are going to be places, if you don't mind, I'm going to draw in some guidelines down here. So those are going to be places where the velocity is 0. If the displacement is minimized or maximized, or is just otherwise not changing, then it's not moving to the left, it's not moving to the right, it must be stopped. So velocity is 0 whenever the displacement is at a minimum or a maximum, or just otherwise levels off. The other thing that I want you to do is identify times when when the slope is greatest, when the slope of the tangent line is greatest, or otherwise where the displacement is changing most rapidly. So I see kind of right at the beginning, it looks like it's changing most rapidly. Somewhere around here, it's changing very rapidly in the downward direction, and again, close or at the end of that graph, it's changing very rapidly. So I'm going to identify those 3 points, and those are places where your velocity is greatest in magnitude, maybe greatest in positive or greatest in negative. So since it's moving to the right and the displacement is increasing, this is a positive velocity over here. Since it's moving backwards, its displacement is decreasing, has a negative velocity in that region. I don't know, so maybe something like that. And since it's increasing again very quickly in this region, then I'm going to draw a dot corresponding to that. It's going to be our greatest velocity. I forgot to draw in my guidelines. That's a good idea to do. And I'll adjust these points as needed. Okay, so. Oops. Okay. So this will help you, I think, a little bit to produce this graph. We now have 5 points on our velocity versus time graph, and basically all we want to do is connect them with a straight, not a straight line, with a smooth curve. And we don't want our velocity in this first region to ever be greater than this value, and we don't want it to ever be greater than this value, and we don't ever want it to be less than this value, so we're just going to connect these with a nice smooth curve. You guys probably know by now that I'm not an artist. So here's a line that, I don't know, maybe approximates the velocity as a function of time. Okay, well, I wanted to find the acceleration versus time as well. Again, what I'm going to suggest that you do is identify key points on your velocity versus time graph. So you can erase these guidelines and pick points where the velocity is minimized or maximized. Looks like those are maybe points where the velocity is minimized, as well as points where it has the greatest slope. Something like that. And I'll put in a couple more guidelines here. Now the places where the velocity is, where the velocity is changing the most don't necessarily correspond to where the velocity is 0. It just happens to nearly work out that way on this sketch that I've drawn. But the really important one is where the velocity is minimized right here. Or if it had been maximized, that would be important as well. Okay, so what do we see from this? Well, the acceleration is, I don't know, low or close to 0 here, and then it decreases, or the velocity decreases and decreases until it reaches a minimum where the acceleration, the slope of the tangent line, is 0. And so where the velocity is minimized, the acceleration is 0. And I don't know, we had a small but maybe non-zero acceleration out here. We have our minimum acceleration maybe right around here. We have our maximum acceleration somewhere around here, because that's where the slope of the tangent line is greatest, and then it kind of levels off again somewhere out here. And so again, we just connect this with a smooth curve, and it maybe looks something like this. And that's it. This completes our graph of acceleration versus time. And so all we did was we started with a graph of displacement versus time, and we found velocity versus time using the slope of the tangent line, and then we found the acceleration as a function of time using the slope of the tangent line. Let me zoom out a little bit. So I finished deleting these extra points. Okay. Let me zoom out a bit, and you can see these three graphs together. And so it's very common to encounter all three graphs one on top of the other, stacked one above the other. So here's our displacement, here's our velocity, and here's our acceleration. I'd like you to take a minute to just look at these graphs and to convince yourself that these are related to one another, and that, oh yeah, this could represent the velocity for this graph, and this could represent the acceleration associated with this graph. One final note. The acceleration is negative, where our graph of displacement is what I'll say is concave downward, and positive, where our graph of displacement is concave upward. And this is true in general. So, again, this might be a little easier to see if I zoom out. Here's our region where the acceleration is negative. Oops. And here's our region where the acceleration is positive. And so if you look all the way back up at our displacement versus time graph, see that the displacement is kind of arching like this in this first region. In your math class, if you're studying parabolas, you might call that a frowny face parabola. And then likewise, in this region out here, the acceleration is positive. And if I look at the concavity of this graph, it's arching upwards, okay? So using just the displacement versus time graph, we can actually determine what our acceleration versus time graph will at least qualitatively look like. It's not going to give us numbers, and you know, it's just basically it's a good check on your work. It's not. I wouldn't go straight from displacement to acceleration. That's tricky. But that's all I wanted to cover in this video, and in the next video we're going to work in the opposite direction. So I'll see you then. Bye bye.